Hi, I'm Dr. Samuel R. Hedeman, and welcome to this lecture called Rocket Thrust, Disproved and Fixed. And basically, a few years ago, I was able to prove that the well-known rocket thrust equation that you can find in almost any physics textbook is wrong. And I proved what the correct one should be, and the purpose of this talk is to explain to you, regardless of your background, why the one in the books is wrong and why the one I discovered is correct. For some background, I'm a quantum physicist and I'm used to solving hard math problems, and I specialize in quantum entanglement. And when I was fresh out of high school, I was a freshman in college, I noticed something amazing. The rocket thrust equation in the textbooks is wrong. And of course, back then I didn't know very much, so I wasn't quite sure. But then many years went by. I eventually got my PhD in physics, and I came back and looked at that rocket thrust equation again, and I said, it's still wrong. So in 2017, I wrote a scientific paper disproving the standard rocket thrust equation, and I showed how to fix it. This paper is called Correction to the Traditional Ideal Rocket Thrust Equation, and you can find it on a repository called Zenodo. Here, I want to make this discovery accessible to everyone, regardless of your background. This talk has two parts. Part one is humans have rockets all wrong, and that's no math or physics background needed. Part two is disproving and fixing the rocket thrust equation, and that you do need some calculus and basic physics to understand. If you're an expert, that's where the juicy part is. However, you should also watch part one because it has a lot of important background for that part too. Now, before we get to it, let's look at a sneak peek. Okay, so a major key to understanding this new discovery is the cops and robbers effect. So basically, when a rocket moves faster than the speed of its own exhaust relative to itself, the exhaust chases the rocket. So let's look at what that looks like. So here we see the exhaust moving to the left, but as the rocket gets faster, there's a point where the exhaust is stationary, and then the point where the exhaust moves to the right, chasing the rocket. So let's watch this again. There's a point, there's a stationary point. Now the rocket exhaust is moving to the right, and it's actually chasing the rocket. So this amazing effect is actually due to some very simple laws of physics. And I'm going to show you exactly how this happens. The traditional textbook rocket thrust equation can't handle this. It doesn't know about this effect. But my new rocket thrust equation exactly accounts for it. So join me now as we explore how this bizarre effect arises. Part 1. Humans have rockets all wrong. And again, no math or physics background is needed for this part. So first, how do rockets move? In space, there's nothing to push on. Okay, so if you're an astronaut out in space, you can't touch anything. There's just vacuum around you, so you can't pull yourself along. Normally when we're walking, we rely on friction because our feet will stick to the ground a little bit, and we're basically pushing the ground behind us, but there's no ground in space. Now, if there's gravitation nearby, like a planet or something, the gravity of the planet can pull you along. But if you're in deep space, there's nothing to touch, so you can't actually move. So imagine you're standing on perfectly frictionless ice. Okay, to bring this back to a more Earth-like example. And apparently, you're a snow person in this example, and let's say you want to move. How would you do it? How would you move? It's perfectly frictionless ice. If you've ever been on ice, you cannot walk on it. You will slip and fall over. And you can't push on the ground to walk. It's just too slippery. But if you throw your scarf, you'll slide in the opposite direction. Okay? You see there's kind of a recoil effect there. So you throw the scarf in one direction and you move in the opposite direction. Rockets move the same way. Okay, but instead of throwing scarves, they use exploded fuel, which we call exhaust. Okay, so here you see this is the exploded fuel, the exhaust coming out of the rocket. It's going to move towards the left, and that will cause the rocket to move to the right with the same recoil effect that we saw above. This effect is called conservation of momentum. But first, what is momentum? Momentum is P equals mv. mass times velocity. Okay, that's what that means. And velocity is basically change in position per change in time. And it's how fast something is going in a certain direction. Okay, and when you talk about direction, you have to specify a coordinate system. Okay, and because of that, it's positive in one direction and negative in the opposite direction. So if the truck were moving to the left, it would have negative velocity. But because it's moving in the same direction that we've designated as positive, it's a positive velocity. Its absolute value is what we would call the speed. So we didn't care about the direction. We would just take the absolute value, and that number would give us the speed. Now, mass is reluctance of an object to change its velocity. And what that means is if you have a big mass, it's hard to move it from rest because rest is zero velocity. And if you're going to increase its velocity, it's hard to change that. But it's also hard to slow it down if it's already moving. And you probably know this. If you've ever run and then tried to slow down really quickly, it's hard to stop your own velocity, hard to get rid of that. And that's what mass measures, this reluctance to changes. Okay, so these two things, m times v, is what momentum is. So conservation of momentum means that the total initial momentum equals the total final momentum for a closed system. And so we can think of this as the total momentum is constant in time, at all points in time. Now let's look at conservation of momentum for you and your scarf. Okay, what this means is that the sum total of the scarf's momentum and yours initially equals the sum total of both of your final momentum. And since P equals mv and you start at rest, that v means P equals 0 for both of you. Okay, so in this case, scarf's momentum is 0, your momentum is 0, so that whole left side there is 0. And what that means is that the sum of the final momentum must also equal 0, okay, by conservation of momentum. So that means in order for that to be true, your momentum must balance the scarf's. Okay, so yours is the negative of the scarf's momentum in that final instance. So in other words, if the scarf is moving in the negative x direction, so there's the scarf moving in the negative x direction, its velocity is negative, okay, and that means mv is negative because m is positive. So the scarf's momentum is negative, so we would draw a little arrow pointed to the left for the scarf's momentum. So that means you must gain that much positive momentum to keep that sum at 0, okay, because you must have the negative of the scarf's momentum. So it's the same length of arrow because it's the same amount of momentum, but the direction is flipped, okay, and that way when you add them together, you get a negative number plus a positive number equals 0, okay, and you don't let that negative sign fool you because the scarf's is negative, negative times negative is a positive. And conservation of momentum is exactly how rockets move. The only difference is that relative motion can cause some interesting and unexpected effects because you're changing the velocity at each instant due to this conservation of momentum. The next time you apply conservation of momentum, that initial velocity is going to cause some different effects to be apparent. So now let's talk about the cops and robbers effect. Imagine robbers in a getaway truck shooting behind them at cops chasing them. Okay, now before they start moving, okay, their velocity in the ground frame is 0. And what that means is as they shoot the bullet out, okay, people standing in the ground will see that bullet move the same speed that someone sitting in the truck would see the bullet move. Okay, and just to give you some definitions here, UREL is the bullet's velocity relative to the gun. We call that the muzzle velocity. And U is the bullet's velocity relative to the ground. That's what the speed that, or the velocity that someone standing on the ground would see. And V is the truck's velocity relative to the ground. Okay, and in this part it's 0. So if the bullet's moving 100 miles an hour to the left relative to the gun, because this isn't moving, it's going to also be 100 miles an hour to the left in the ground frame. So that's pretty straightforward. Now when they start moving, but their speed is less than the muzzle speed, so let's say they're going maybe 20 miles an hour, because that's less than 100 miles an hour. The relative motion means that the bullet's initial speed is the truck's speed. So if they're going 20 miles an hour to the right, the bullet before it gets fired is also moving 20 miles an hour to the right. So when it gets shot 100 miles an hour relative to the gun, it must overcome this initial speed. So the initial speed is 20. It'll be 20 minus 100, which is negative 80. Okay, and what that negative means is that the bullet's still going to move towards the left, but it's only going to have 80 miles an hour in the ground frame. Okay, because it had to overcome its own initial speed with the truck. And that's relative motion. That's the relative motion effect here that we call Galilean relativity. Now, what happens when that truck speeds up so that it's moving 100 miles an hour? It has the muzzle speed of the gun relative to the ground. Okay, so when the truck's speed is the same as the bullet's muzzle speed, something amazing happens. An observer standing on the ground would just see that bullet fall straight down. Okay, because now the bullet has 100 miles an hour to the right to overcome, but it's only moving 100 miles an hour relative to that gun. So that means we've got 100 miles an hour minus 100 miles an hour equals 0. Okay, so this is a really interesting effect, and if you were watching, it would look like the gun in the truck just got out of the bullet's way, and it were hovering there for a second right before it fell to the ground. Okay, so the speed of the bullet relative to the ground is 0 in the x direction. Okay, so that's really interesting. What happens when the truck moves faster than that? Okay, so faster than that, the bullet's muzzle velocity can't overcome its initial velocity from the truck. Okay, so now let's say the truck's moving 120 miles an hour to the right. Well, the bullet can only move 100 miles an hour relative to that truck, relative to the gun. So it's going to have 120 miles an hour to start, minus 100, it's still going to be plus 20 at the end. And that plus 20, the plus means that the bullet's going to be moving to the right now. It's going to chase after the truck. So the bullet actually chases the robbers. And that's the cops and robbers effect. Ejecting something behind you when you're moving faster than it's ejected means it will follow you. Now it's still going to be butt first, meaning it's still going to be pointed to the left, but its motion in the ground frame is going to be to the right. Okay? And if the robbers slow down suddenly after they shoot, their own bullets could hit them, which is kind of funny. So how does this relate to rockets? So the cops and robbers effect makes thrust weaker as a rocket gets faster. So if the rocket's speed relative to the ground is faster than its exhaust relative to itself, it'll be like we just saw, where the exhaust acts like a bullet chasing the robbers. The exhaust will be moving forward as the rocket moves forward. And because of that, the exhaust is moving in the plus x direction, its velocity will also be positive. And that means that the exhaust has a positive momentum because it's a positive number velocity times positive mass. So the momentum of the exhaust is a positive number in this case. So by conservation of momentum, the rocket must gain an equal amount of negative momentum to balance it out. And that means if the rocket started out with some momentum p, you're going to have p plus that negative momentum, so that the final momentum of the rocket is p minus pe. It's decreased by that amount because it gained negative momentum. So the rocket's exhaust actually lowers its momentum in this case, and therefore it acts as a drag force. However, its velocity still increases. Okay, and that's because m, the mass, is decreasing typically, such that p equals mv also decreases even though v is increasing. Okay, so there's a little counterintuitive. The rocket's still going to speed up even as its momentum is being lowered and even as the thrust is acting as a drag force. Okay, because of conservation of momentum, we have this bizarre situation where the v still increases. Okay, because it's the decreasing m that is really responsible for the lowering of the momentum in this case. Now imagine that the rocket just shoots out one mass blob at a time. Okay, so same velocity relative to itself, same muzzle velocity, each in equal time apart. So let's see what that looks like. So this equals equally spaced in time and the same mass and the same relative velocity. And I'm just applying conservation of momentum here to see what each new velocity of the rocket should be. Okay, and then I'm taking that into account also to find the final velocity of each expelled exhaust blob. Okay, so this is just very basic rules of physics applied to find how this motion arises here. Now, if we wait until the rocket's speed in s in the ground frame is faster than its exhaust relative to itself, then we have the same situation, okay? And now it's going to be like the cops and robbers, where the bullet's almost stationary and then the bullet chases the robbers, okay? And that's because the speed of the rocket increases until the relative speed of the exhaust cannot overcome the initial velocity that the exhaust has with the rocket before it leaves the rocket, okay? And it's really just the cops and robbers effect. It's the same thing. So it's the cops and robbers effect. And again, the simulation only used conservation of momentum and Galilean velocity addition. Okay, so I use very, very basic principles here. And normally we use Newton's laws, which are called equations of motion, to find out how things move. But because we will see soon that textbooks use them wrongly, I wanted to avoid Newton's laws for this simulation. So I only used conservation of momentum and Galilean velocity addition so we could see what really happens. Okay, so now let's compare the traditional textbook thrust to my new thrust. So suppose we have a rocket sending out equal mass blobs in equal times, just like the simulation we just saw, so that the function of mass as a function of time is a stepwise linear function. And if we graph the momentum of the rocket versus time using only conservation of momentum, we get this shape. Okay, so this is each time a mass blob leaves, the momentum of the rocket increases. Okay, so then another mass blob leaves after an equal amount of time and the momentum of the rocket increases. So it's going to keep increasing like this. And notice this sort of takes into effect what we just saw, right? There's a time when the momentum of the rocket barely increases at all, and that's when the exhaust leaving it has basically zero velocity. And then after that, the momentum of the rocket's going to start to decrease, okay, because the blob that leaves it is moving in the plus direction. It's following the rocket. So as we let the time intervals go to zero, the exhaust gets closer to continuous, so that mass function becomes more like a line. And if we look at the momentum of the rocket, this same shape is going to get smoother and smoother, okay? And note that here I kept the total mass ejected the same in each one of these situations. So as I let the time interval get closer to zero, we're ejecting a smaller amount of mass each time, but the total amount is going to be the same. That's why these look so similar. So now let's look at the textbook thrust. What does it predict? Okay, so we can use the textbook thrust to figure out what the momentum of the rocket should be. And it turns out that it predicts a constant value for this situation. Now don't worry about the math of this formula yet, okay? We'll talk about this in the advanced section more. But basically you can think of this formula as the push that the rocket feels from its exhaust according to textbooks. So let's look at what happens to the rocket's momentum based on this textbook thrust. And because it's a constant, it's going to cause a linear increase in the momentum. Okay, this is what the textbook says should happen. But the actual momentum of the rocket based on conservation of momentum is totally different. Now, if we only looked at a small amount of time, they would seem to agree, only approximately. But we can see that they're way different overall. Okay, so the textbook is totally wrong because it's not obeying conservation of momentum. It doesn't even have, it's saying there's an increase when momentum is decreasing. It's totally wrong. So they don't agree. And this means that the textbook thrust is definitely wrong. Okay, even though this is just one example, that's sufficient to prove that the textbook is wrong. Now for experts watching, calculation of momentum from a thrust force like this is the same regardless of which version of Newton's second law we use. And that's the advantage of this particular example, is that because it's a constant, either of these will give the same. So you can't say I somehow sabotaged it by using one or the other. They both give the same wrong result in this case. So the textbook is definitely wrong. Now let's check what my thrust formula does. So here's my thrust formula. And don't worry about the math of this. We're going to look at that later in the advanced section, but the little star means that it's different. Okay, that's just to distinguish it from the textbook. So again, don't worry about the math. We explain that later. But for now, we can just think of this as taking the cops and robbers effect into account. So if we want to plot this for the momentum of the rocket versus time, okay, this is the dark blue, the thin dark blue line here is the momentum of the rocket due to this new thrust force. And we see that this new thrust exactly causes the same momentum as the actual momentum of the rocket. Okay, it's exactly predicted. So my new thrust formula is exactly correct. And furthermore, my predicted critical time, T sub c, okay, which is this vertical line here, exactly matches the critical point of the actual momentum. Okay, so the actual momentum, the light blue curve here, is increasing, and then it stops increasing and then starts decreasing. And my theoretical critical time exactly predicts that transition. Okay, so I didn't just look at the numbers here and then find this critical point. I actually have an equation that you can use to find this exact time. Okay, so my theory exactly predicts this behavior, and the textbook is oblivious to it. Okay, so this is a big success all the way around. So our conclusion is the textbook thrust is wrong and the new thrust is correct. We've just demonstrated by example that the textbook thrust is wrong, and that is sufficient. We only need one example to show that it fails. We've also demonstrated by example that my new thrust is correct. Now, one example is not sufficient to prove that it's correct, but in the advanced section, I will prove that it's correct in all cases. The textbook thrust is wrong because it uses the wrong form of Newton's second law, F equals ma, which is only valid for constant mass. The rocket thrust formula has been wrong for over 200 years. Okay, people just keep copying the same wrong thing. And it's used by every space agency in the world, even when they admit that the other form of Newton's second law is correct, F equals dp dt. The problem is that while they admit that's correct, they're not consistent with it, and they end up effectively using F equals ma. This may cause billions of dollars to be wasted through wrong conclusions. My new thrust formula works because I use the correct form of Newton's second law, F equals dp dt, and that's valid for time-changing mass. And I'm consistent about it. So that's the end of the simple part. Okay, so if that's all you need to see, thanks for watching. If you know some math and are ready for some juicier details, keep watching and buckle up, it's about to get interesting. Part 2, disproving and fixing the rocket thrust equation. And calculus and basic physics are needed for this part. This part basically has two sections. The first section, we're going to review Newton's second law and derive an important concept called impulse. This is important because Newton's second law really is the issue which causes all the textbooks to have the wrong equation, and that's what we really need to revisit. In the second part, we're going to use that concept to disprove the textbook thrust and also to prove my new thrust is true in all cases. So first, recalling the textbook rocket equations, we have the standard setup, and see my paper for the full reminder of this derivation. I'm not going to go over every little step. I'm just going to generally recap it here so you can get the main points. It's an ideal rocket, and there's no external forces. There's no, it's non-special relativistic, and the exhaust is constant relative velocity, VREL. Okay, and I say no external forces, there's going to be, the rocket thrust is the external force, but there's no other external forces, no gravity or anything like that. And we want to treat the rocket and exhaust system as a system of constant mass to allow F equals ma on that system, or at least that's the standard way that the textbook sets it up, and that's totally valid to do that. And then they use conservation of momentum, and then they solve for the quantity ma. And you can do that. This is true. You can solve for ma given that setup of the problem. Then they mess up. They identify ma as thrust and call that the first rocket equation, and that's dead wrong. But that's what they do, and that's where we're getting the thrust equation. So this is the same in every textbook. Maybe they'll use different symbols and everything, but this is the same result that they get. Then they rearrange, basically time integrating the ma equation for the velocity. And this is called the second rocket equation. And in fact, 1 and 3 here, this ma equation and v, are both correct. They're both correct. But 2, this identification of ma as the thrust is wrong. It's a misidentification of the thrust. So the problem is that most experts don't understand which form of Newton's second law to use, F equals ma or F equals dp dt. So the problem is that most people trust F equals ma more because they learn that before they learn F equals dp dt. Okay, textbooks usually start with ma and work you up to dp dt. Also, since people learn it as beginners, they're shakier on it than they realize. It's like the first thing they learn, and then they go off in their own directions, and then they never really got solid on it. F equals dp dt is definitely more general than F equals ma. Okay, by the product rule of derivatives, if you take the derivative of momentum, you're going to use that product rule, and you're going to get 2 terms. Okay, and we can call dv dt the acceleration, a, and you can instantly see that if dm dt, the time derivative of mass, is 0, then this will just be F equals ma. Okay, so that means that F equals ma is a special case of F equals dp dt, and it's where dm dt is 0. And in other words, whenever you have a time derivative b equals 0, that means that F equals ma is only valid for objects with constant mass. Most people know the above. They intellectually know it. They can do that derivation. The trouble is, when people do this, they start trying to plug in velocity like vrel. They try to plug in that relative velocity there. They start trying to make arguments. They say, well, it's relativistic. They call dp dt the relativistic form, and they confuse themselves. P is the momentum of the object of interest, okay? So v is the object's velocity. So you can't just go plugging in relative velocity to that. That's just wrong. But people confuse themselves by trying to jump in and plug things in, and that's just not consistent. Or they rationalize that isolating ma in one is correct because they're just so used to having equals ma on one side of the equation in Newton's second law. And really, most people just copy examples when they're learning, and they think that means they know it. They're really not thinking about the problem. So we're going to actually derive F equals dp dt here. But first, let's see some examples of why the wrong use of F equals ma is so hard to change. So by using the textbook thrust, all textbooks and all space agencies still effectively use F equals ma for rockets, despite the fact that dm dt is non-zero for a rocket. Many papers, Wikipedia, etc., all wrongly claim that F cannot equal dp dt for rockets. So, and this is dp dt, just expanded. But they actually say this in many cases. And one particular case that's pretty obvious is this small published response to a different article. And this published response is titled F does not equal dp dt, where they actually wrote in mv for p there. And this one rationalizes that it's wrong because the system itself is changing. And the truth is that systems often change in conservation of momentum problems. And the fact that it's changing is actually why F equals dp dt is correct. And I'm just going to foreshadow what I'll show you here soon. Newton's second law is for open systems. You know, we're all concerned about the external forces acting on the body, meaning that the environment is exchanging momentum and energy with the body. Otherwise, Newton's second law would be pretty boring. So it's inherently open, and that's okay. The system can change. Another example is this article on the use and abuse of Newton's second law for variable mass problems. And this was on a NASA website. And it rationalizes that it's wrong because it violates Galilean relativity. The truth is that F equals dp/dt is actually the only version of Newton's second law that satisfies both Galilean relativity and conservation of momentum, which we saw with the examples in part 1. Okay, remember the textbook 1 did not give the proper momentum, and it wasn't consistent with relativity. Okay, and that's why it didn't account for the Kopson-Roberts effect. So in Newton's Principia, he called mass a quantity of matter. Okay, and we have this equation, m equals the density times the volume, which we all know. And in his words, that was density and bulk conjunctly. Okay, and I put this here so that we can see the word conjunctly means times. He means multiplication there. And bulk means volume. Okay, so it's very clear what his words mean in that case. He then defines this quantity called quantity of motion, which we know as momentum. And that means motion, in his terminology, equals mv. And here's his words for this quantity of motion. He calls it velocity and quantity of matter conjunctly. Okay, so velocity is clear, that's v. Quantity of matter he defined right before that, which we can see clearly as mass, and conjunctly means time. So velocity and quantity of matter conjunctly is mv. Okay, so clearly what he means by quantity of motion is momentum. Okay, and a little bit later in his Principia, he has law 2. Okay, and keeping in mind that motion equals mv, which is what we call p for momentum, he says the alteration of motion is ever proportional to the motive force impressed. Alteration of motion means the time rate of change of the motion, and which is momentum, which we've just shown. So dp/dt is what he said, alteration of momentum, and is ever proportional to the motive force equals F, where F is the sum of all external forces on the body. And that means F equals dp/dt according to Newton. Okay, so this isn't a derivation. Okay, I'm just going back to Newton's own words so that we know that he really was talking about momentum. And now we're going to stay tuned for a derivation of this, but first, we want to ask, how did our blatant misconception of Newton's second law happen? Okay, so textbooks start by grouping exhaust and rocket as the system. Okay, so that's the system that textbooks use. That system's mass is constant, and n, the forces on it, is always 0. But they isolate ma, where that mass changes with time, and call it the thrust force. So the problem is they aren't consistent about using F equals ma for constant mass. They acknowledge it has to have constant mass at one point, and then immediately forget that conveniently because they're so excited because they found ma. But if the rocket equation is wrong, how did we get to the moon or Pluto? I mean, I'm sure a lot of people are thinking, well, if it's wrong, how come things work anyway? And the thing is, engineers don't trust theory, okay? And that's because even if we have a correct theory, even if it's perfect, we can't take everything into account in the universe. There's just not enough information that we can handle. Even if we could get it all, we don't have powerful enough computers to handle it all. So we just can't do that. So even a proper theory can't work perfectly. And so what they do to deal with this is they use measure and correct feedback to fix a rocket's trajectory continuously. Or another way to do it would be to just do many, many tests and build up empirical models and build mathematical models that reflect the data. But that's different than having a good theoretical understanding. Okay, and it's really bad if you've got the wrong equation to start with. Okay, then you're really you have to work overtime to correct something because your theory is wrong to begin with. So it looks like we understand rockets because this kind of fixing as we go along makes it seem like we have a handle on it, but we really don't. So why is this important if we still get rockets to work? People say, well, at the end of the day, we still get the job done, so what does it matter? The reason is because it means we've been judging rocket designs incorrectly, at least potentially, okay? And for example, a major metric of a rocket goodness is thrust to weight ratio. But if the thrust equation we have is wrong, and it is, then it really makes me doubt, and it should make everyone doubt, that those goodness metrics are accurate and are being applied correctly. Because if you don't know what thrust is, maybe your calculations for your data are wrong. Maybe you're putting data into wrong equations. So that translates into huge wastes in budgets. Okay, good ideas thrown away, bad ideas kept. So how do we fix this? First, let's derive Newton's second law so we can better understand and better trust dp/dt. So here we're going to talk about how to derive Newton's second law. So we start with conservation of momentum for a closed system, right? Sum of all initial momenta equals the sum of all final momenta. Okay, and we write that more simply like this, and we can bring the left over to the right and recognize the delta. So delta P equals 0. Okay, so that's for a closed system, and it's very straightforward. By the fundamental theorem of calculus, then, we could write that delta P as a sum over dP, where that prime here is just a dummy prime. Okay, it's not a derivative. And then we can insert 1 in a clever way, dt over dt in the integrand, and then regroup that dp over dt and bring the dt over and switch the limits of integration. Okay, and we have delta P equals the integral over dp dt from initial time to final time. And what this means is that the sum over the quantity dp dt completely determines delta P, okay, unless the bounds are equal. If the bounds are equal, that's a trivial case. Okay, then dp dt doesn't affect anything, but that integral is always 0. So we can ignore that trivial case. The only non-trivial ways that dp or that delta P can be 0 are if dp dt is 0 for all time, okay, then that integrand is always 0. So in that case, delta P is always going to be 0. So P is constant, right, because that's what dp dt equals 0 means, and that's a closed system, okay. And the other way that delta P can be 0 is if the sum over non-zero dp dt is still 0, okay. And how could that happen? That would be if the system lost some momentum and then gained the exact same momentum back over the time period of interest. That way delta P would be 0, but P would not be constant. Okay, so that is an exchange of momentum with the environment. So that's an open system, but there's no net delta P. Okay, but instantaneously there is a delta P if you look on a short enough time scale. And the only way that delta P can be non-zero for a given time scale is if dp dt is non-zero for at least some times, and the sum over dp dt is non-zero, obviously. Okay, so delta P is non-zero and P is not constant. Both imply that we have an open system, okay, that there's an exchange of momentum with the environment, and the net momentum is non-zero. Okay, so it's not a balanced exchange. So both of these cases, there's an exchange of momentum with the environment. That's an open system. So Newton realized that a closed system could not change its momentum, which we showed above. So if an object's momentum changes, then something external forced it to change. And I'm being provocative with the language there. So he called dp dt the net external force. Okay, he named it a force. And here, of course, F means the sum of all external forces acting on the body. Okay, and this, I call this the Newton's full second law. It really is just Newton's second law. It's the true second law. Net, because he knew momentum is a vector. Okay, so dp dt is also a vector, and so force is a vector as well, so it obeys superposition, and that's why we can write up the sum of all forces there. and external, meaning that it's external to the object of mass m, whose momentum is p equals mv. Okay. And a little note here, once the mass leaves the rocket, okay, it's external to the rocket. Okay. So the force it imparts is an external force. Okay, so once mass leaves the rocket, yes, the system has changed, but that very leaving is an external force acting on the rocket of the mass m of t. So from 4, we can immediately derive impulse, right? We just write the definition from 4 and put a dt on both sides, switch to dummy variables, integrate over time, and we see that the dt's cancel. You get integral over dp, and you get the delta there, okay? And that immediately gives us impulse equals delta p, okay, where the integral over the force, time integral, is the impulse, okay? And we can think of this as conservation of momentum for an open system, right? Because if that impulse is 0, we get delta p equals 0, which is a closed system, okay, or it's an open system with balanced exchange. But this is like a general equation that holds for both open and closed systems, and so we can call this an open system conservation of momentum. So now we want to find a test whether or not a given thrust force F is correct. And we can actually use the idea of impulse. So we usually write impulse as J, and I write J sub F so we know what force is defining an impulse here. Okay, so the impulse of force F is the time integral over that F. And it gives delta P due to that F as that. Okay, it's just really rewriting the impulse definition. Now the rocket equations give us the instantaneous momentum, okay, correctly. Because m of t can really be any realistic function as long as it's decreasing, because we're talking about a rocket. And the second ideal rocket equation for v of t, which we've already seen earlier, is correct. So we know v of t, we have m of t, okay, at least in theory, and we can plug them in. And that means we know the left side of 1, delta p, is just this, right? Because we can plug in v of t to the final momentum, and we have the initial momentum there, and we know m of t, right? Because that can be any function. So when we rearrange this a little bit, we get this delta p, and we can get this from the textbook equations. Okay, there's nothing fancy here. So this we definitely know is the correct delta p. And this actually gives us a test for F. Okay, to see if a given F is correct, plug it into the right side of 1, okay, plug it in there, take its impulse, and see if it gives back the proper delta P from 3 here, okay? If it's the correct thrust force, it must do this. So let's prove now that the textbook rocket thrusts is wrong, okay? The textbook rocket thrust, which we saw earlier, is this. We now want to subject it to this test. We see if its impulse gives back delta P. So we take its impulse, okay, so plugging it in, just plugged it right into the integral there, and VREL is a constant in the textbook problem, and minus sign, so those constants come right out of the integral, and now we can just cancel those dt's, and this integral is very simple, and notice I changed the bounds as you must, and you end up with minus VREL times delta M. Okay, and that's the impulse according to the textbook thrust. And it's not correct because it's not the delta P that we just derived. And as we showed in the last slide, that delta P is a much more complicated function. It has a natural log, and this delta M in the first term is times the initial velocity, whereas here the delta M is times minus VREL. So it's just totally wrong. It's nothing like it. So this means that the textbook thrust is definitely wrong because it violates conservation of momentum, and it gives the wrong impulse. So now we want to do the same test for my new thrust, but first we have to show how we even get the new thrust. So how to derive the correct thrust. First, we're going to use Newton's second law, the real one. And I give a star to this thrust, okay, and it's the only force on the rocket. So there's only one force, and I give the star to distinguish it, that's all. And so dp dt, you just expand p, you use the product rule, as I've already mentioned, and we get this form, which is exactly what so many papers and sources say that you can't do. Well, all I'm doing is following Newton's second law to the letter. And we want to recall the textbook velocity equation, which is correct. Remember, this is the same equation we've used to get delta p. And recall that the MA equation, also from the textbook derivation, where I've written A as dv dt, okay, is this. Now, this is correct again, right? MA is still MA. It's just the identification of this as thrust that's wrong. This isn't the thrust. This is just MA. So we can use both of these. We can plug both of these in. So we can plug V of t there, and we can plug m dv dt over there. Or if you prefer, you don't like this equation, maybe you could plug V here and just take its time derivative. Both of those are equivalent. And you will get this when you do that. Okay, so there's the V plugged in, and there's MA plugged in that second term. Okay, and then I just pull out a dm dt and regroup some stuff in here, and this is the new thrust equation. Okay, this is what I claim the true thrust is for a rocket. So now we want to subject that to the same test that we subjected the textbook thrust to. So we start by getting the impulse of our new thrust. So there's the impulse of it. And now here I just plug the whole thing in. Okay, and notice that includes the dm dt on the end. And what we're going to do to start this out is expand the ln of that fraction. Okay, so we just use our log laws there. And now we're going to distribute. Okay, so I've just distributed dm dt to these two main terms in here. And then we're going to distribute the integral, okay, to each main term. And now I'm going to distribute dm dt into each one of these terms over here. Okay. And now I'm going to distribute this integral to each one of these terms in here. Okay. And now we can see that we have some common integral types here. So that's a very simple integral. So is that. So is that. Those are the same. Here's the only one that's a little bit different. So first, let's simplify the integrals. Okay, we get rid of the dt over dt in each one. Okay, and now this is the only one where, you know, you might not remember it exactly. So we're going to use that identity up there, which is something you can look up if you've forgotten it. And so there's that identity plugged in, and the other ones were just simply delta m. Those were very easy integrals. And now I'm going to just expand this that integral right there, because it has evaluated at the endpoints. Okay, so that in parentheses here, there's the upper limit minus the lower limit version of it. And now we just want to distribute and simplify. We've got a lot of group terms and minus signs. So here I just distributed the minus sign there, and here in this little bracketed term I distributed the minus sign. So that's what happened there. And now I've got another minus sign to distribute in this term. So I'm going to do that. Okay, so I've just distributed it there. And now at this point we can see that we have some things that cancel. This minus mi plus mi, m of t here, and ln mi times mi is canceling this. Okay, so all of those cancellations will get us to here. And now notice there's a common m of t, okay, in each one of those terms. So I'm going to pull that out, and I'm going to put this vi over here, right? So it looks like we like to write m's before v's. Okay, and now I just use log laws to bring that into a common log, and we get this expression for the impulse due to the new thrust that I derived. Now recall the correct delta P is exactly that same quantity. Okay, we have a perfect match for delta P now. So comparing those two things, the impulse of the new thrust gives the correct delta P, so the new thrust gives the correct impulse. Okay, so that proves that this is in fact the correct thrust due to the rocket's exhaust. So to conclude, We've proved the textbook rocket thrust equation wrong because its impulse does not give the correct momentum change. We've proved our new rocket thrust is correct because its impulse does give the correct momentum change. And therefore, over 200 years of textbook and research have been wrong. And that's not an unprecedented thing. That happens a lot. With special relativity, before Einstein, people just assumed that time passed the same rate in all reference frames. And it was an unconscious assumption that everyone shared for hundreds of years, and it was wrong. So this is not something that is impossible. It's quite possible for everyone to be wrong for a long time. But now we finally have the correct rocket equations. And of course, see my paper for full details about that. And in the paper, instead of focusing on momentum like we did with the plots here, I plot force. Okay, and you can see in this picture from the paper that this dotted red line up here is the textbook thrust, and this solid blue line is my new thrust. And you can see that the new thrust starts out positive, passes through 0 at the critical time, and then becomes negative. So that's the thrust acting as a drag on the rocket, as I mentioned earlier, and that's because of the cops and robbers effect. And during this portion, the exhaust is actually chasing the rocket. Okay, and of course, the textbook is oblivious to that critical time there. And so the paper includes generalizations as well, such as time-changing relative velocity. And it also treats energy because energy comes from F equals ma in the textbook version. So you can't use the work kinetic energy theorem in its present form in a book. You have to rederive it for time-changing mass, which I do in the paper. And that we do a separate test, and we again confirm that the new thrust is correct. And the paper also goes into how to include other forces. And this is because a lot of times, especially like you'll see on websites and textbooks, when they include gravity, they just add the gravitational acceleration to the regular acceleration, and you can't really do that. You have to start from Newton's second law and add it as a sum of the forces acting on the object. That's the correct way to do it. And you get a slightly different answer when you do it that way. So that's it. Thank you very much for your interest in this, and I hope you enjoyed it. A big problem that I've had getting this published is that reviewers haven't really been reading the paper thoroughly, or at all in some cases, perhaps in most cases. And I think the reason is everyone's really busy and it's just convenient not to give things the full focus. But they seem to think that I'm rederiving the textbook thrust. And they're like, we already know this. But on page 1 of the paper, I put the word wrong next to the textbook thrust when I'm just, doing a little review of that in the beginning. And if the referees are not seeing that and it's on the first page, it really makes it look like they're not reading it. And that's a big problem in science. And it's not just this paper, it's pretty ubiquitous throughout all of science, is that referees are not really doing the job they should be doing. So I hope this encourages you to do a more thorough job, actually maybe work through the examples in the paper. And I hope this also illuminates what the paper is saying. Everything we've covered here is basically the first 2 pages of the paper. So thank you very much, and I hope this encourages everyone to never take what's written in a book at face value. Always rethink things and work through them yourself in great detail. All right, thank you very much.